Hi friends, welcome to Mickey Techie. Learn as an engineer, teach as a champion. I would like to thank my family for continuous support for creating these kinds of technical videos and uploading in the public domain. I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore. And I would like to thank Almighty for my good health and my mind. And I would like to thank all my subscribers and followers for their continuous support and watching my video for a long. Today's topic of interest is springs. First of all, I would like to quote a very good example for a springs where it is used. Whenever we need a sophistication, there we need some amount of stiffness. When there is some amount of suspension, we need. For an example, if we take a vehicle, we want to make our journey comfortable, we need a good suspension for our vehicle. In suspension, what are all the things to be there? We know that we can easily visualize that there is a spring is there is a shock absorber is there. Shock absorber is nothing but a damper. It is for a damping purpose. And what is the purpose of a spring? It is used to absorb the strain energy or an energy due to resilience. First of all, the spring is a very good elastic body. Springs are the elastic bodies which absorb energy due to resilience. So, with this definition, I would like to quote a thing that the springs will be working up to the elastic limit because resilience means the energy absorbed, strain energy absorbed by a body up to the proportional limit or an elastic limit is the definition. Therefore, the springs are very good at elastic limit. Therefore, the springs are said as an elastic body. They can absorb strain energy as much as they are capable of. Okay, and we have a, different types of springs. Here, I would like to quote only two types of the springs. One is a laminated or a leaf spring. You can easily visualize wherever the heavy vehicle is there. You can see the leaf springs. There is a one master leaf. It is having a maximum length and other are the supportive links. So master link and supportive links are coupled together for making a complete a leaf spring. They are they we can say it as a laminated springs because each springs are laminated by means of a bolt and nut or a tie bar. And the another type of a spring is a helical coil spring. In the helical coil spring, we have a closed coil as well as open coil helical springs. Why the helical springs are called as a helical? Because they are coiled into helix. Helical springs are thick springs. First of all, you have to note this thick spring wire coiled into helix. That is why it is called as a helical springs. Now we are interested in seeing closed coil helical spring. Closed coil means the helix angle is very small. The pitch between two adjacent turn are small. If in a open coil spring the helix angle is somewhat is larger and pitch between two adjacent turns is somewhat there. In the closed coil helical spring, bending effective on spring is ignored, whereas in the open coil helical spring, bending is there. If you can see a long helical spring, when you are interested to compress, there we have a definite C of buckling over there, buckling over the spring. In the open coil, there is a problem, whereas in the closed coil, there is no bending effect, so it is ignored. Next, the closed coil helical spring stands purely torsional shear stress, as well as the open coil will also stand purely torsional shear stress. Here, I would like to quote an equation, the torsional equation. The springs as well as the shafts are working in this equation, that is T by J is equal to C theta by L is equal to tau by R, which means T is the torque, J is the polar moment of inertia, C is the modulus, shear modulus, and theta is the angle of twist, and L is the length of the spring or shaft, and tau is the shear stress, and R is the radius. Here, the same equation, same governing equation for spring as well as the shaft, both are failed by means of shear stress. Therefore, the placement of shear stress is very important. That is why here we are comparing the shear stress for the shaft as well as spring. For the shaft, the outermost fiber will having a maximum shear stress, whereas at the center it is zero. That is why the solid shafts are preferred over the hollow shafts. Hollow shafts are preferred over the solid shafts. Solid shaft will give a huge weight to the power ratio, whereas the hollow shafts will give more power to the weight ratio. Okay, hollow shafts are generally low weight, solid shafts are generally having high weight. Whereas in the springs, the innermost fiber will having a more shear stress and the outermost fiber having a very less shear stress. Here we are going to see some of the formulas. These three formulas are very important for the springs. So we are going to discuss. These formulas are derived from the torsional equation. T by J is equal to C theta by L is equal to tau by R. Here, the maximum shear stress induced in the wire tau max is equal to 16 WR capital R divided by pi into d cube, where W is the axial load, capital R is the mean radius of the coil, small d is the wire diameter, and small n is the number of turns, and C is the modulus of rigidity. We can use C or G. Next one is a very important formula, deflection of the springs. Deflection delta is equal to 64 WR cube N divided by C d power 4. We can say in terms of R in terms of D, we can replace R in terms of D. Then the equation becomes 8W d cube N divided by C d power 4. And next is the stiffness of the spring. We know that stiffness is equal to load by deflection. Therefore, stiffness K is equal to C d power 4 divided by 64 R cube N. And next, we are going to discuss an important terms like spring index. Spring index, it is notated as a C. Spring index is the ratio of the maximum diameter, that is the coil diameter to the wire diameter. Mean diameter of the spring coil to the diameter of the wire is known as spring index. According to the spring index, the size of the spring, size and stiffness of the spring we are doing. Therefore, the stiffness or deflection is directly proportional to the spring index. We have noticed in the previous equation, the stiffness is equal to small d by capital D. Therefore, stiffness is inversely proportional to spring index. Whereas the deflection, you can easily visualize that there is a d by d ratio. Therefore, deflection is directly proportional to the spring index. Also, the shear stress, you can see the relation R by D relation. Therefore, shear stress is directly proportional to the spring index C, whereas stiffness is inversely proportional to spring index C. What it means that if the stiffness is more, the spring index is less. If the spring index is less, then the stiffness is more. Next is the solid length. Length of the spring L is equal to number of turns into coil diameter. And this is the very important formula, the modified stress distribution suggested by A.M. Wall. The Wall is a very good engineer, mechanical engineer and a scientist. He found that there is a correction factor. This correction factor will take care of the stress concentration over the curvature effect as well as the direct stress effect. So that is what he found, that Wall's correction factor as a K, whereas the shear stress equation becomes tau is equal to 8p capital D divided by pi into small d into K. Here P is nothing but load. What the notation we W here we are indicated in P. That is what, that is the very simple thing. So 8 W D K divided by pi into small d cube. Here K is equal to Wall's correction factor. It is 4c minus 1 divided by 4c minus 4 plus 0.615 divided by c, that is equal to spring index Wall correction factor K. Next, a very important thing, we have different types of orientations of the spring. Here first type is the series spring. Series springs, the figure is representing, here you have a one spring, it is coupled directly to the another spring. This is called as a series of the spring. And if the springs are connected by means of a parallel one, it is a parallel spring. Where you can see is in the parallel springs, for an example, if you have a Bajaj vehicles, Platina and a Discover, you will have a spring in spring suspension. You can notice in the from the advertisement, spring in spring suspension. That is, one spring is inside the another spring. One spring is inside the another spring. Spring in spring. That means it is mounted as a parallel one. Whereas if you take an engine, open an engine, if you see a valves and valve guides are coupled with by means of a spring. There is both SNS spring is there, parallel spring is there, concentric spring, parallel spring or concentric spring is there. It is calculated by means of a parallel one. Whereas you take it as a TVS Victor, new type of TVS Victor, you can see the series springs are there. There is a one spring on the top and another spring on the bottom. They are in different stiffnesses. So from this, the suspension may vary. The suspension as well as the comfort may vary. If you can drive, if you are having a chance to drive both the TVS Victor as well as the Platina spring in spring suspension, you can see that definitely you can see and feel the suspension and good amount of the stiffness which the two vehicles are having. Okay, here we are going to discuss by means of a formula how the equivalent spring stiffness is calculating. In the series, 1 by K equivalent is equal to 1 by K1 plus 1 by K2, and K1 and K2 are the stiffnesses of the series springs. If you simplify this equation, K equivalent is equal to K1 K2 divided by K1 plus K2. Where in the parallel springs, if K equivalent is equal to K1 plus K2, K1 and K2 are the stiffnesses of the both springs. Here we are going to discuss some of the important formulas and important concepts. A simple spring is cut into two halves, then the stiffness of the spring will becomes 2 times of the original stiffness. That is, If you cut a spring in equal halves, what will happen? Then the stiffness is becomes 2 times, double the time. If the cutted springs are parallel, if it is cutted springs are placed between as a parallel springs, then the stiffness becomes 4 times. Okay, and the strain energy stored is half into load into delta, half into load into theta. Theta is the angle of deviation. Here, for your reference, I have indicated if this spring is cut in two halves and placed parallel, and the stiffness, equivalent stiffness, is increased by 4 times, whereas the spring is cutted by means of a 4 parts and kept parallel, and the stiffness is increased by 16 times. From this relation, you can notice that how can we simply increase the stiffness of the spring by means of a parallel, and also by means of the cutting the springs. Next, spring and spring. In the spring and spring, I have mentioned that two concentric springs are mounted. You can notice that very interesting phenomena is there. One spring is in right helix and another spring is in left helix. Why? Because if there is a suspension, if there is a compression, the springs are tend to buckle. What happen if the inner spring is more buckle and merge to the outer spring coil? It won't work. The suspension won't work. That is why the same helical turns. This is the problem. The both right helix will jam at some point. That is why instead of jamming that problem, we are using both right helix and left helix in the spring and spring or a concentric spring position. Whereas next one, the long springs are subjected to compression load, it tend to buckle. This is the very important thing. If you see the bike front fork, if you have a chance to open the front fork, if you can see a very huge open coil helical spring is there. Without the pipe, what will happen? It tend to buckle. Without the external pipe, it tend to buckle. That is why the front fork are made up of a pipe and the back fork is not made up of a pipe. Since back fork the spring length is very small, and that is why it is given as a open end. Whereas the front fork the length is very huge, and without the pipe the suspension will bend or a spring will tend to buckle, and you won't feel the comfortness. I would thank you for watching. I hope that you have an enjoyable section. Please, if you have any doubts, please let me know in the comment box. You can share the video and you can subscribe and like this video. Thank you.